These are the answers to the AP Chemistry packet that is entitled Unit 1, Summative Assessment Practice. On this slide, you can see Unit 1 at a glance. Unit 1 is entitled Atomic Structure and Properties. In this video, I will present practice problems that cover all of the topics in Unit 1. This video should help you to prepare for the Unit 1 summative assessment. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Okay, let's get started. The instructions that you see on this slide are the same instructions that you will see on the AP Chemistry free response section. Show your work for each question in the space provided. Examples and equations may be included in your responses where appropriate. For calculations, clearly show the method used and the steps involved in arriving at your answers. You must show your work to receive credit for your answer. Pay attention to significant figures. Question 1 says the following.
A student needs to measure a sample of 0.0375 moles of potassium chlorate, KClO3, for an experiment. Calculate the mass in grams of KClO3 that should be measured. So let's start by calculating the molar mass of KClO3 from the information on the periodic table. So if we add up the atomic masses of potassium, chlorine, and oxygen times 3, it's 122.55 grams per mole. Then we're going to write down the number of moles that we were given in this problem, which 0.0375 happens to have 3 significant figures. And then we're going to use the molar mass as a conversion factor to go from moles to grams. So moles on the bottom, grams on top. When we do this math by multiplying by 122.55, we get a number which has not been rounded yet. So rounding off to 3 significant figures, this becomes 4.59 would not be rounding properly, so we'll say 4.60. Again, that would be 3 significant figures. All right, let's take a look at question 2. Calculate the number of molecules of methylamine, CH3NH2, that are present in 0.86 grams of methylamine. So let's figure out the molar mass of methylamine, again, using the information from the periodic table. So we have 1 carbon, 5 hydrogens, and 1 nitrogen. So we add up the atomic masses for all those elements, and we get 31.06 grams per mole. We're going to start with grams, so 0.86 grams of methylamine. That has 2 significant figures. First, we're going to go from grams to moles using the molar mass as a conversion factor, so grams on the bottom, moles on top. And now we're going to use Avogadro's number to go from moles to molecules. So 1 mole on the bottom and Avogadro's number on the top. So we'll divide by the molar mass, multiply by Avogadro's number. So our unrounded answer in terms of number of molecules of methylamine looks like that. But since 0.86 only has 2 significant figures, let's round this off to 2 significant figures, 1.7 times 10 to the 22 molecules of methylamine. Okay, let's take a look at number 3. Based on the information above, this is a mass spectrum for an element, and we don't know at this point what the identity of the element is yet. Part A, calculate the average atomic mass of this element. So I see 1 peak at mass number 85, and the abundance is 72.2%. I see another peak at mass number 87, and the abundance is 27.8%. So we'll calculate the weighted average to get the atomic mass of this element. So 85 times 0.722 plus 87 times 0.278. Now that we know the average atomic mass, 85.556, part B asks, what is the most likely identity of this element? Let's go ahead and consult the periodic table. And the element that has an atomic mass that falls between 85 and 86 is rubidium, which has the atomic symbol Rb. So that's rubidium. Its atomic mass is very similar to what we calculated, 85.5 approximately. And now in part C, fill in the table below for the two naturally occurring isotopes of this element. So we know the mass number is either 85 or 87. Let's go back and look at the periodic table. How many protons does rubidium have? Atomic number 37, so that's 37 protons. So there's our mass numbers. They each have 37 protons, and since protons plus neutrons equals the mass number, 85 minus 37, or 87 minus 37, will give us the number of neutrons. So number of neutrons are either 48 or 50. All right, let's move on to question number 4. So we are told that the element gallium, Ga, occurs naturally as a mixture of two stable isotopes. Information about one of the two naturally occurring isotopes of gallium is shown in the table above. Part A. What is the average atomic mass of gallium? Let's go ahead and use the periodic table to figure that out. So gallium's average atomic mass is 69.72. Now to fill in the missing information in the table above, at this point we don't know the other mass number for the other isotope of gallium, but we do know that there are only two stable isotopes that occur naturally. Since the total abundance has to be 100%, 100 minus 61 will give us 39%. So we know that's the abundance of the other isotope. But now to figure out the mass number, let's go ahead and set up an algebraic equation which is based on the formula for calculating the average atomic mass. So at this point we're going to go ahead and just call the other mass number x. We know that 69 times the percent abundance as a decimal, so 0.61, plus x, which we don't know yet, times the percent abundance as a decimal, 0.39, equals the average atomic mass that comes from the periodic table. And now we'll just do the algebra to solve for x. So I multiplied, and now I have to subtract 42.09 from both sides of the equation. And then I'll divide both sides by 0.39. And even though 70.8 is a number with a decimal, we're looking for a whole number, a mass number as a whole number, so that's close to the number 71. All right, question 5 says, calculate the percent composition by mass for each element in phenylhydrazine, C6H8N2. So let's determine the molar mass, or the formula mass, for C6H8N2. So carbon, atomic mass 12.01, and we have 6 of them. Hydrogen, atomic mass 1.008, and we have 8 of them. Nitrogen 14.01, and we have 2 nitrogens. So 108.144, that is our molar mass or our formula mass in AMU. The percentage of carbon by mass is the total mass of carbon in the compound, so 12.01 times 6, divided by the total mass of the compound itself, or the formula mass, times 100. 66.63% carbon by mass. We do a similar calculation for hydrogen and for nitrogen. So the percentage of hydrogen by mass is 7.46%, and the percentage of nitrogen by mass is 25.91%. Question 6. A certain compound has the following percent composition by mass. Determine the empirical formula of this compound. So the first step in the calculation is to assume that we have 100 grams of this particular sample. That way we can just turn all of these percentage values directly into grams. So we have 19.02 grams of carbon, 4.79 grams of hydrogen, and 76.19 grams of sulfur. Let's convert from grams to moles using the periodic table. So we divide by the atomic mass of carbon. We get 1.584 moles of carbon. We're just going to leave that number for a moment. We'll come back to it. And then we're going to use the same procedure for hydrogen and sulfur. Again, remember, I've talked about this in previous videos, that even though hydrogen is an example of a diatomic element, in this case, we are not taking the diatomic nature of hydrogen into account. These are individual atoms of carbon, hydrogen, and sulfur. So we're dividing by the atomic mass of hydrogen, not the formula mass of H2, which is how it would exist naturally as hydrogen gas. All right, if we do this math, we get moles of hydrogen, and then we'll finish it off with converting sulfur from grams to moles. So now at this point, we have three different numbers for moles of C, H, and S. Since the 1.584 moles of carbon is the smallest of the three values, we're going to divide each value of moles by that particular value. So we get 1 for carbon by dividing by itself. We get 3 for hydrogen. And then interestingly enough, we get 1.5 when we do that same calculation for sulfur. So we don't want to round that value just up to 2 as a whole number. We actually need to do something different. And I've talked about this before. We're looking for whole numbers. But 1.5 is right there halfway between 1 and 2. So how do we get whole numbers from 1, 3, and 5? Well, we just multiply each and every value by 2. So now the whole numbers for carbon, hydrogen, and sulfur are 2, 6, and 3. And then those represent the subscripts in our empirical formula. So the empirical formula of this compound is C2H6S3. Okay, this is question 7. It will also ask us to calculate an empirical formula, but it's going to be a little bit different. We are not given the percentage of each element by mass. We are given some combustion data. So we know the mass of the sample that was burned, and we know how much CO2 and H2O is produced in terms of grams. 17.25 gram sample of a compound containing C, H, and O is burned completely in excess oxygen. Data from the combustion experiment is shown in the table above. Part A, determine the mass of carbon present in 17.25 gram of the compound. Well, since all of the carbon that was originally present in this compound has been converted into carbon dioxide, CO2, we're going to start with the 29.17 grams of CO2. And up on the corner of the slide, I've done the molar mass calculation for CO2. So we can go from grams of CO2 to grams of carbon, in that there are 12.01 grams of carbon for every 44.01 grams of CO2. So there is that calculation set up, and we get 7.960. We'll go with 4 significant figures because 29.17 has 4 significant figures, so 7.960 grams of carbon. If you are thinking, what if I had taken the CO2 and first converted it into moles of CO2? That would be fine. Your next step would be to go from moles of CO2 to moles of carbon, which is a 1-to-1 ratio, and then finally to grams of carbon. So from the periodic table, you're going to get the same answer either way. So I'm showing you 2 different approaches to calculate the number of grams of carbon that is present in 29.17 grams of CO2. All right, on to part B of this question. So a similar strategy, determine the mass of hydrogen present in this compound. All of the hydrogen has been converted into H2O. So the molar mass of H2O, I'll put that up on the slide in the upper right corner. Now, 11.94 grams of H2O, we're going to convert that into grams of hydrogen. There are 2 H's in the formula H2O. So there are 2.016 grams of hydrogen for every 18.016 grams of water. We do that math and we get, when rounded off to 4 significant figures based on the 11.94 having 4 sig figs, we get 1.336 grams of hydrogen. Again, like I said before, had you first converted grams to moles, you could do that. So grams of water to moles of water. There are 2 moles of hydrogen atoms for every 1 mole of water molecules. And then finally, we could convert that to grams of individual hydrogen atoms. We would get the exact same answer. All right, now that we know grams of C and grams of H, we can figure out the number of grams of O in part C. So we have our answer to part A, our answer to part B. So the mass of oxygen present in 17.25 grams of this compound is just going to be the difference. As we subtract the grams of carbon and the grams of hydrogen, then the rest of the mass is coming from oxygen. So 17.25 minus 7.960 grams of carbon minus 1.336 grams of hydrogen gives us a value of 7.95 grams of oxygen. 7.95 grams of oxygen. I rounded off to 2 decimal places because I was limited by 17.25. When you subtract, you always go with the least number of decimal places. All right, let's move on to part D of this question. Determine the empirical formula of the compound. Well, we know grams of C, grams of H, and grams of O. Let's convert each of these from grams to moles. So divide by the atomic mass of carbon, divide by the atomic mass of hydrogen, divide by the atomic mass of oxygen. So now we are looking at moles of C, moles of H, and moles of O. Of these 3 values, since the 0.497 moles of oxygen is the smallest of the 3 values, let's go ahead and divide each value of moles by 0.497. So we do that for carbon and we get 1.33. I'm not going to round it. We do that for hydrogen and we get 2.67. Again, I'm not going to round it. And obviously for oxygen, we divide that by itself, we get 1. So earlier we talked about how 1.5 was doubled. A number that ends in 0.5, if you multiply by 2, then you get a whole number. But here, 0.33 and 0.67, we should multiply by 3 so we can get a whole number set for our empirical formula. So watch what happens. We multiply each of these number of moles by 3. 4 moles of carbon for every 8 moles of hydrogen for every 3 moles of oxygen. So those are the subscripts. C4H8O3 is our empirical formula. Okay, this is number 8, a mixture of CaCl2, calcium chloride, and CaSO4, calcium sulfate, contains 28.25% chlorine by mass. Calculate the percentage of calcium chloride by mass in this mixture. So let's assume that the total mass of the mixture is equal to 100 grams. That way the percentage, 28.25, is now the grams of chlorine present in this mixture. The molar mass of calcium chloride can be determined by the periodic table. We have calcium times 1, chlorine times 2. So there are 70.9 grams of chlorine for every 110.98 grams of calcium chloride. The 28.25, I'm going to start with that. That's grams of chlorine. I'm going to put grams of chlorine on the bottom and grams of calcium chloride on the top. So based on the information from the periodic table, there's 110.98 grams of calcium chloride for every 70.90 grams of chlorine. So I do that math, and I get 44.22 grams of calcium chloride. Well, the percentage of calcium chloride by mass, because we assume the total mass of the mixture is 100 grams, would be 44.22 divided by 100. So our answer to number 8 is 44.22% calcium chloride by mass. All right, moving on to number 9. A mixture has a mass of 13.50 grams and contains 5.25 grams of sodium nitrate, NaNO3, and 8.25 grams of sodium carbonate, Na2CO3. Calculate the percentage of sodium by mass in this mixture. Well, there are 2 components of this mixture, the sodium nitrate and the sodium carbonate, and each of them contains sodium. So what we have to do is figure out how many grams of sodium are in sodium nitrate in this mixture, and how many grams of sodium are in the sodium carbonate in this mixture. So let's go ahead and think about the molar mass calculations for sodium nitrate. Again, using the periodic table, we have 1 sodium, 1 nitrogen, and 3 oxygens for a grand total of 85.00 grams per mole. For the sodium carbonate, We have 2 sodiums, 1 carbon, and 3 oxygens, grand total of 105.99 grams of sodium carbonate per mole. So let's take them one at a time. There's 5.25 grams of sodium nitrate in the mixture. Let's calculate how many grams of sodium there are using the information from the periodic table. There's 22.99 grams of sodium for every 85.00 grams of sodium nitrate. I'm going to write that number down and come back to it. So that was 1.420 grams of sodium. And now let's repeat that same process but using 8.25 grams of sodium carbonate. Grams of sodium carbonate on the bottom, grams of sodium on the top. Remember that there are 2 sodiums in the formula. So it's 45.98 grams of sodium for every 105.99 grams of sodium carbonate. Do that math, and we get 3.579 grams of sodium. Now that we've calculated all of the sodium present from the sodium nitrate and the sodium present from the sodium carbonate, we can add them together. And if we do that, we get almost exactly 5 grams, 4.999 grams of sodium. The total mass of the mixture is 13.50. So mass of sodium divided by the mass of the mixture times 100. And our answer to number 9, the percentage of sodium by mass in the mixture, works out to be 37.03% sodium by mass in this mixture. All right, number 10, write the ground state electron configuration for each of the following. We have 2 different atoms and we have 2 different ions. Let's start with strontium, Sr. Remember that for electron configuration, it's the distribution of the electrons in an atom or an ion among the various orbitals or shells or subshells, and these patterns on the periodic table help us to write the electron configuration of an element or an ion. So starting with strontium, Sr, atomic number 38, let's see how we can get there. So starting at the top of the periodic table, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Almost done. The last little part would be 5s2, and that is the complete electron configuration for strontium. You could also abbreviate it by using the noble gas krypton, which takes care of 36 electrons, followed by the last part, the valence electron shell, 5s2. Now, for strontium 2+, it is an ion which has lost 2 electrons. So remember, when electrons are removed from an atom to form a cation, they are always removed from the occupied orbitals having the largest principal quantum number, n, or the energy level, which in this case is 5s2. So they go away, and now we're left with everything that krypton has. But we can't just write krypton in brackets as our answer. So we have to go back to the previous noble gas, which would be argon. Argon would be 18 electrons plus 4s2, 3d10, 4p6. That would be the electron configuration in the shortened form. Again, this is strontium 2+, which has a total of 36 electrons. All right, let's go find zinc on the periodic table. Zinc has 30 electrons, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then finally 3d10, because we go all the way to the end of that section. So there's the full configuration. You can abbreviate with the noble gas argon. Again, that would be 18 electrons for argon, followed by 4s2, 3d10. There's the long form and the short form of zinc. We're going to lose 2 electrons from zinc to form a 2+ ion. Remember that for a transition metal, it loses electrons from the valence s orbitals, which means we're going to take it from 4s, not 3d. So when those 4s electrons go away, we're left with 1s2, 2s2, 2p6, 3s2, 3p6, and 3d10. If we abbreviate using argon as the noble gas, it would just be the 3d10 after that abbreviation. Okay, this is number 11. We are given the photoelectron spectrum, or the PES diagram, for an element. Write the correct symbol for the element that is represented by the PES diagram above. Starting from left to right, it's going to be 1s for the first peak, 2s, and then 2p for the next part, 3s, 3p, and then finally 4s. So we can literally read the electron configuration for this element from left to right. We know that the number of electrons in each shell or subshell is determined by the height of the peak. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, which, if we look on the periodic table, that corresponds to the element calcium. So the identity of the element is calcium. All right, this is number 12. This time, we are not given the complete photoelectron spectrum of an element. We're given a partial photoelectron spectrum. Now, we know this is fluorine, but it says draw the missing peak that corresponds to the electrons in the 2p sublevel. So fluorine has a total of 9 electrons, 1s2, 2s2, and 2p5. On the partial PES diagram, we have the 1s2, the 2s2, but we have to draw the 2p5 peak. Now the 2p sublevel is slightly higher in energy than the 2s sublevel, and what does that mean? Well, it means that those electrons are going to be easier to remove, therefore they should have a lower binding energy. So where are we going to draw this peak? It would be to the right of the 2s peak that's already on the diagram. How high the peak should be is determined by the number of electrons in that subshell. So we have 5 electrons in the 2p sublevel or subshell, so therefore we're going to make that peak go up to 5 notches on the diagram. So that red peak that I have drawn on the slide, that would be an acceptable response to this particular question.
All right, question 13. Which element, sulfur or chlorine, has a smaller value for its atomic radius? Justify your answer in terms of atomic structure and Coulomb's law. So remember that we're not just going to simply state a periodic trend that atomic radius decreases from left to right. We're not going to simply mention something about electrons or protons without giving the whole story. So in terms of Coulomb's law has to do with both magnitude of charge and distance between the charged particles. When we are comparing the atoms of 2 different elements in the same period, so like we're doing now with sulfur and chlorine, we should take a look at the electrons and where they are located in terms of the energy levels. So sulfur has 16 electrons, chlorine has 17 electrons. The electron configuration of these 2 elements are very similar. For sulfur, 1s2, 2s2, 2p6, 3s2, and 3p4. So sulfur has 6 valence electrons that are located in energy level 3. Chlorine has 7 valence electrons that are also located in energy level 3. So the valence electrons of each atom are located in the same energy level. The difference between them has to do with the number of protons in the nucleus. That's going to be the important part of our answer. So when comparing the atoms of 2 different elements that are located in the same period, the valence electrons of each atom are located in the same energy level. The element with more protons has a greater nuclear charge, and there is a stronger attraction between the nucleus and the valence electrons, so that would cause a stronger attraction. Now we're talking about atomic radius here. That's going to make chlorine smaller in size. The smaller atomic radius would be for chlorine because the electrons are more strongly attracted toward the nucleus. So as you can see, I've mentioned the electron configuration of each element, talked about what they have in common, same energy level for the outer shell electrons. Chlorine has more protons, greater nuclear charge, stronger attraction toward the nucleus, and chlorine has the smaller atomic radius. All right, question 14. Ionization energy is defined as the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms or ions in their ground states. Removing the outermost electron from a neutral atom is called the first ionization energy and is represented by the following equation. Which element, sulfur or selenium, has a greater value for its first ionization energy? Justify your answer in terms of atomic structure and Coulomb's law. So just like in number 13, we're not going to simply invoke a periodic trend and say ionization energy decreases from top to bottom. We're going to take a look at the electrons, where they are located, and decide what's our best strategy. So these are the two elements, sulfur and selenium. They are in the same column or group. The electron configuration, which I'm abbreviating here, the noble gas abbreviation for sulfur, so neon, 3s2, 3p4, and then for selenium, it's going to be argon, 4s2, 3d10, 4p4. So whenever we have two elements that are located in the same group, the valence electrons are located in different energy levels, and that's going to be the important part of our explanation. We are comparing the outer shell for level 3 with the outer shell for level 4. So when comparing the atoms of two different elements that are located in the same group, the valence electrons of each atom are located in different energy levels. Electrons located in a higher energy level are farther away from the nucleus. Electrons located in a lower energy level are closer to the nucleus. So according to Coulomb's law, the smaller the distance between oppositely charged particles, the greater the attractive force. So we're not arguing for atomic radius like we were in number 13. We're talking about the first ionization energy. So again, to summarize, there are the electron configurations of sulfur and selenium. We're talking about which element has a greater value for its first ionization energy. The answer is that sulfur will have a greater value for its first ionization energy because these electrons are located in a lower energy level that is closer to the nucleus. The electrons are more strongly attracted toward the nucleus. All right, this is question 15. And here we are talking about another periodic trend. We've talked about atomic radius and ionization energy. This is electronegativity. The three elements that we are comparing are carbon, nitrogen, and silicon. We don't need to justify our answer in terms of why, but we do need to actually rank them in order from smallest to largest electronegativity. Let's take a look at where these elements are located and the periodic trend for electronegativity. So carbon and nitrogen are in the same period, carbon and silicon are in the same group, and in general, electronegativity values tend to increase as we move from left to right across a period, and they tend to decrease as we move from top to bottom down a group. So for these particular elements, nitrogen being further to the right has a higher electronegativity than carbon, and silicon being further down the group has a lower electronegativity than carbon. So it's going to be silicon as the lowest and then nitrogen as the highest. So again, that is our answer to number 15, but we did not have to justify why in terms of atomic structure and Coulomb's law. All right, this is question 16. Now we're talking about ionization energy, but this time it's successive values of ionization energy for the same element. So we're removing multiple electrons from this element X, and so what we have to look for is a pattern. Part A, how many valence electrons does element X have? Justify your answer. So while these values for ionization energy are increasing with each successive electron that's being removed, the valence electrons can be distinguished from the core electrons. So 578, 1,817, 2,745, and now there's a really large increase, 11,577. So that's when all of the valence electrons have been removed, and we are now removing an electron from the inner shell or the core electrons, which, because they are much closer to the nucleus, require more energy to remove. So the answer to part A is that this particular element has 3 valence electrons because there is a big increase in the ionization energy when the 4th electron is removed. This is because the inner shell core electrons are much closer to the nucleus and require much more energy to remove. Moving on to part B, write the empirical formula of the compound that should be formed between element X and oxygen. Justify your answer. So now that we know that element X has 3 valence electrons, we can go find that particular group on the periodic table and talk about how it would combine with an element such as oxygen. So we've talked about this pattern before in terms of the valence electrons. You can see from left to right, 1 through 8 as labeled in yellow, and then 1 plus, 2 plus, 3 plus, and so forth, 3 minus, 2 minus, the charge on the ions. So for an element that is located in this particular column, whether that's boron, aluminum, gallium, indium, 3 valence electrons, it would normally form an ion with a charge of 3 plus. Oxygen would normally form an ion with a charge of 2 minus. So to put them together, a 3 plus and a 2 minus, we would need a total charge of either positive 6 or negative 6 to make a balanced formula for those ions. So we would need 2 ions of element X and 3 ions of oxygen, and that formula would be X2O3. So that's going to be our answer to part B of this question. Element X has 3 valence electrons, would normally carry a 3 plus charge when it becomes an ion. Oxygen normally carries a 2 minus charge when it becomes an ion, so the empirical formula is X2O3 because the sum of the charges on the ions should equal 0. All right, moving on to part C of this question. A certain element that is located in period 2 of the periodic table has the same number of valence electrons as element X. Right, the symbol of this element, again, we know where to find periods and groups on the periodic table. So the group would be group 13, the boron, aluminum, gallium, indium, that particular family or that group. And then period 2 is the second horizontal row. So we have now identified that element B, boron, would have that number of valence electrons. So correct answer is boron. All right, well, that brings us to the end of this question as well as the Unit 1 summative assessment practice. I hope that these answers and explanations were helpful. Good luck studying for your Unit 1 summative assessment. Thanks for watching.